There is one device standing between an electrical overload and a fire. It sits at the front of almost every panel and every distribution board on the planet. When the current climbs too high, it does its job in a fraction of a second. It trips, it kills the power, and then you switch it back on once the fault is cleared. That device is the circuit breaker. In this video, I will explain what a circuit breaker actually is and how it works. The two trip mechanisms hiding inside it. The difference between an MCB and an MCCB. Trip curves, and why it is the single most important protective device in a control panel. Let's open one up. Quick note before we dig in. This is from PLC Simulator, where you can practice PLC and panel skills free, right in your browser. No install, no hardware. The link is in the description. Click the link in the description to try it free. Now, back to the breaker. Start with the job. A circuit breaker is an automatic switch. Under normal current, it stays closed and lets power through, exactly like a switch you left on. But it is constantly watching the current. The moment that current climbs past its rating, an overload or a short, the breaker interrupts it. It opens the contacts and stops the flow. And here's the part that matters in the real world. After it trips, you reset it. Clear the fault, flip the lever back to on, and it works again. Now compare that to a fuse. A fuse does the same job, overcurrent protection, but it is a one-time sacrificial part. A thin element inside it melts, breaks the circuit, and then it is dead. You throw it away and fit a new one. Breaker trips and resets. Fuse melts and gets replaced. Same goal, different mechanism. So how does the breaker actually decide to trip? There are two mechanisms inside, and they handle two very different problems. The first is the thermal element. It is a bimetal strip, two different metals bonded together. The clever bit is that the two metals expand at different rates when they heat up. Under a sustained overload, say a motor pulling a bit more current than it should, the strip heats up. Because one metal grows faster than the other, the strip bends. Bend it far enough, and it releases the latch and trips the breaker. The key word is sustained. This is a slow, deliberate trip with a built-in delay. A brief, harmless surge will not trip it, but a real, lasting overload will. Thermal protection is forgiving, and it is exactly what you want for the slow stuff. The second mechanism is the magnetic element, and it is the opposite of the thermal one. It is a coil, an electromagnet, that the load current flows through. Under normal current, its pull is weak and nothing happens. But a short circuit is not a gentle overload. It is a massive, instant spike of current, many times the rating. That spike drives a huge magnetic field in the coil, and that field is strong enough to snap the contacts open almost instantly. No delay. No waiting for anything to heat up. Milliseconds. So the two work together. Thermal handles the slow, sustained overloads. Magnetic handles the violent short circuits. A standard breaker has both built into the one device. Now the types you will actually meet. The small one, the one clicked onto a DN rail in a panel or a home consumer unit, is an MCB, a miniature circuit breaker, typically rated up to about 125 amps. For bigger loads, and the main incomer you step up to an MCCB, a molded case circuit breaker, is physically larger and rated for much higher current. And then there is the trip curve, marked right on the breaker. Type B, Type C, and Type D. The curve sets how much inrush the magnetic element will tolerate before it fires. Type B trips fast for resistive loads like heaters and lighting. Type C allows more inrush for motors that gulp current at startup. Type D tolerates the most for transformers and heavy motors with a big switch-on surge. Pick the wrong curve and you get nuisance tripping or no protection at all. So where does all this live? In a control panel, breakers are arranged in a hierarchy. One main breaker sits at the incomer and protects the whole panel. Then branch breakers sit downstream, one per circuit. The point of that structure is selectivity. A fault on one branch should trip only that branch breaker, leaving the rest of the machine running. It should not take out the main and kill everything. That is coordination, and it is half of good panel design. The other half is grounding, so a fault current has a safe path back and trips the breaker fast instead of energizing a frame. I have a full walkthrough of an electrical control panel and a separate video on grounding, both linked below. So here's what to walk away with. A circuit breaker is an automatic, resettable switch that protects against overcurrent, unlike a fuse, which melts once and is gone. Inside it, two mechanisms: a thermal bimetal strip for slow, sustained overloads, and a magnetic coil that snaps open instantly on a short circuit. MCBs are the small DN rail breakers, and MCCBs the big ones. The trip curve, B, C, or D, sets how much inrush it tolerates. Get that, and every breaker in every panel stops being a mystery. Now, go make it concrete. If you want to practice PLC and panel skills hands-on, click the link in the description to start free at plcsimulationsoftware.com. No hardware, no install. Subscribe, new video every Tuesday. See you in the next one.